Hi and welcome to Lecture 5. In this video we are going to talk about the Bayesian t-test. We'll do a little bit of the theoretical background of how the t-test is developed in a Bayesian sense, and then we'll demonstrate how to perform the Bayesian t-test in JASP, particularly using the summary statistics module. So in order to get started, let's recall what a t-test does. Remember that the t-test arises anytime that you want to compare some observed sample mean or pair of sample means to some hypothesized standard, let's say mu. And this can be generalized to one of three different situations. First, as stated, we can look at the one sample t-test, and the example that we do today will be similar to that. You can generalize this a little bit more if you have multiple, let's say 2 measures per observed person, then you can consider that as a paired samples t-test, and then you take the difference in those scores, and that's your sample that you're comparing to a hypothesized mean of 0. And then similarly, you can extend this to 2 independent groups and consider the independent samples t-test. So each of these works a little bit differently, but at their core, they're all the same basic idea. We're taking some sort of sample mean and comparing it to a hypothesized population mean. So let's go forward with an example that we can carry through today. So let's suppose that we are interested in assessing the effectiveness of some mathematics instruction program. And after implementing that program, we measured some mathematical ability in our participants. And we're going to use this scale. This is a fictional scale, but let's say that it's called the Scale for Advancing Mathematical Ability. So we'll call that the SAMA. And that's a national assessment with a known mean score of 50. So 50 is average performance in mathematics according to this test. Now our sample, who has had this training, this mathematics instruction program, they got a mean of 54.4. All right, so they're a little bit above the national average, and their observed standard deviation was 10. And so, of course, the question that we might ask at this point is, did the training work? Did the training change? Did our sample have a different mean than would be expected from the population? Okay. Now, the Bayesian approach to answering a question like that, we know from the previous 4 videos, is that what we want to do is build and compare 2 models about the population level effect size. Now, this is a little bit different. Remember, effect size is nothing more than the observed difference in the means scaled or divided by the standard deviation. And so you'll notice I'm using a Greek letter delta here. This is the Greek version of the letter D, which is what you typically see in your statistics courses. Remember Cohen's D. Well, what the Bayesian t-test is going to do is consider a couple of models on this effect size. Okay, the first model, the null model, is going to say that effect size delta is equal to 0. That is, there was no difference, no observed effect after the treatment. On the other hand, the alternative hypothesis would be that this hypothesized population level effect size delta is not equal to 0. That is, that the effect size is non-zero. And so this is a really good way to parameterize this problem, because effect size is something that folks in the behavioral sciences know something about. If you see an effect size of 1, that's a really big effect. If you see an effect size of 0.2, that's a small effect. So we have some intuition about effect sizes. And so it makes sense to code our problem about the t-test directly move it from t-scores and expected means and standard deviations together to just combine all of those into one quantity called effect size. So that's going to be a little bit different compared to lecture 4, where we built our models directly on correlation. We're going to build them on effect size here. So those are our models. So with those models, we have 2 goals. Okay. The first, of course, is do model comparisons. So we want to figure out which of these models, the null or the alternative, H0 or H1, is the best predictor of our observed data. And we do this with the Bayes factor. In this case, the Bayes factor for model 1 over model 0 would be the probability of the observed data under H1 compared to the probability of the observed data under H0. And then, if the alternative is preferred, that is, if the effect size is not equal to 0, then we can estimate what that effect size is using the posterior distribution for our quantity delta under the alternative hypothesis. Now remember, technically, Bayesian inference requires us to specify a prior on the parameter of interest. We've seen that through multiple lectures now. In the first few lectures, we talked about priors on the population level probability of success on each trial when we were using binomial models. In the previous lecture, lecture 4, we talked about specifying priors on the population level correlation. Now, with our t-test, since we are dealing with the parameter of effect size at the population level, this delta, we need to specify a prior on delta. So how would we do that? Okay. Well, recall that there are two types of priors that we consider in the context of Bayesian inference. Now, we covered this in lecture 4, but let's quickly go back over it. There's priors on the models, and then there's priors on the parameters within the given model. Now, when we talk about priors on models, remember we're asking, before observing data, what's the relative likelihood of the two competing models, H0 and H1? As always, our common default is that we set them equal to each other. That is, we give them 1-to-1 prior odds. And then those prior model probabilities are updated after observing data via the following very nice Bayesian relationship. That is that the posterior odds for, let's say, H1 over H0 is going to equal your prior odds, 1-to-1, times the Bayes factor. So in this case, when you use this default, that is 1-to-1 prior odds, the Bayes factor is your posterior odds. We'll use that in just a short minute. And the way that works, of course, is then that lets you find the posterior probability of either of your models. In this case, I have H0 written down, but it could be the probability of H1 given the data. Either way, you find the posterior odds for that model, and then you divide by 1 plus the posterior odds. Now, more important for our discussion today is the notion of priors on parameters within the given model. So remember, our model definitions were the null hypothesis is delta equals 0, that is 0 effect, whereas H1 is that delta is non-zero. So this is what we're interested in here, because if delta is non-zero, there's a lot of different ways to be non-zero. We have to ask ourselves, what exactly do we mean by this statement? How do we get a handle on the uncertainty that a statement like this provides? And of course, the answer is we quantify our uncertainty about this effect size delta under H1 by placing a distribution on it. Now you'll remember in lecture 4, this was an easy thing. In fact, in all of the lectures leading up to here, this was actually an easy thing to do. If you didn't know anything about the parameter of interest, you could just place a uniform distribution on it, right? That worked very nicely for binomial parameters because they could only range from 0 to 1. It also worked really nicely for correlations because correlations can only range from -1 to +1. And so because that range of possible values for your parameter is bounded, it's easy to place a uniform distribution on it and say every possible parameter value is equally likely. In this case, that won't work. So delta, this population effect size, is theoretically unbounded, right? It could go anywhere from negative infinity, that is as negative as you like, to as positive as you like. And so placing a uniform prior will not work because that would have to be a uniform prior of infinite width, which would then have 0 height, which really wouldn't make a lot of sense for us. So we have to be a little bit more clever about how we define a default prior in this case. The uniform prior will not work. And so there's a few classic approaches that I want to walk through the development of that will actually lead us to what the modern default prior for the t-test is. So the classic approach would be to place what's called a normal prior on delta. So you can see down below we've got this little normal distribution centered at 0 and with a standard deviation of 1. And so this would say that most effect sizes would be in the 0 range, but of course we do have the possibility of having some positive effect sizes. In fact, given that in the normal distribution, let's make a little sketch here, that since 68% of the curve is between -1 and +1 in terms of standard deviations, then this is actually saying that there's a 68% probability that your effect size is between -1 and +1. Okay, so I mean this is a reasonable a priori assumption, right? We would assume that most of our effect sizes that we would expect to observe would be somewhere, you know, in the less than 1 in magnitude range. Now certainly this prior, let me get rid of those marks, this prior does admit the possibility of having very large effects, you know, out here in the 2, 4, and 6 range, as well as very large negative effects. But relative to, you know, the central mass of this, these are not very likely at all. Okay, so this is one approach, and this approach is often given the name the unit information prior. If you get to reading some of the older literature developing Bayes factors in our discipline, you'll see mention of the unit information prior a lot. And that's what this is. Okay, it's just simply place a normal distribution centered at 0 with a standard deviation of 1. And you can actually make JASP do this. It doesn't do it by default, as you'll see why in a second, but you can, and it's a reasonably good solution. Okay. But now there are some analysts who do not like this approach because they think this is not a good default approach. It places almost too much constraint, too much information on the effect size, at least on the prior for the effect size. So is there a way to kind of relax some of the very specific types of assumptions we're making? For example, could we relax the assumption that this has to equal 1? Could we let that standard deviation vary a little bit? And the answer is yes, we can. Okay, so this was the approach taken by Zellner and Siow in 1980. And what they did was they said, let's let the prior be even more objective by letting this variance freely vary. So what they then said is, let's do this in 2 stages. Let's let delta vary as a normal distribution centered at 0, but with a variable variance. Okay. Now, of course, we've got to somehow specify this variance. And so what Zellner and Siow did is they said, well, let's just put another prior on that parameter, on that variance itself. The prior that they placed was what's called an inverse chi-squared distribution. It looks something like this. And so here, this distribution puts most of your variances in the 0 to 1 range, but does admit even larger variances. Now, that seems complicated. This becomes now what's called a hierarchical model because you're placing a prior on the effect size that depends on another parameter that has a prior on it. And so this hierarchical model specification seems complicated, but Liang et al. In 2008 figured out that if you look at that hierarchical model specification and you just what's called integrate it out, so that's a calculus term for basically letting it vary and then taking the weighted average across all the values of delta, you actually end up with a mathematical distribution that's reasonably easy to deal with. It's called a Cauchy prior. So C-A-U-C-H-Y is pronounced Cauchy. Cauchy was a mathematician in the 1800s who did a lot of things, and as a result, his name is placed on this prior. Now, what's important for you to know in practice is that this Cauchy prior differs from the normal prior in a couple of important ways. Okay, first of all, notice that it is not as peaked at 0 as the normal distribution is. It also has fatter tails than the normal distribution. Now, that may not seem like a thing that you would want to happen, but it turns out that the Cauchy distribution is actually one of the better priors that you can place as a default on these t-test situations, because it also lets the test have a number of desirable properties with respect to Bayesian inference. Now, those properties are a little bit too specific and technical for us to get into in this introductory level video, so I'm going to leave it for now, but just know that the Cauchy prior, in all of its weirdness, is actually mathematically and conceptually preferred as a prior over just the normal distribution. So the reason it works out really well for us is because under this Cauchy prior, so Jeff Rauter and his colleagues in 2009 showed that you can actually directly compute the Bayes factor from the observed t-score and the observed degrees of freedom using basically this equation right here. Now, what's that C? Well, C is really complicated. I didn't even want to write it on the lecture. It's a really complicated constant, that requires some numerical routines to do integration. So C has to be approximated by a computer software. And so in JASP, you're going to see an approximation column, and that's where it comes from. It's an approximation of that constant. But everything else under the hood is just a square root of something that you compute. This whole procedure is called the JZS Bayes factor, and it's what's implemented by default in JASP. What is JZS? Well, J stands for Harold Jeffreys. It's also the same J that's in JASP. Okay, so Harold Jeffreys is a very important figure in the development of these Bayes factor ideas that we have been talking about. And then the Z and S you just saw a second ago, that's from Zellner and Seow, because the Cauchy prior comes from basically collapsing that procedure that Zellner and Seow came up with. So if nothing else, know that the prior that we use in JASP for the t-test is called the Cauchy prior. If you ever ask yourself or someone else asks you why the Cauchy prior, you can go back and follow through this chain of logic. It comes from the fact that if we use a normal prior with an unspecified variance and then let the variance have a prior distribution, namely as an inverse chi-square, squashing those two together gives you this solid line Cauchy distribution. Okay, so that's enough technical stuff. Let's go back to our working example, and then we'll show how to work that in JASP. So recall that in our example, we gave a bunch of people who took a mathematics training course, we gave them a test, and let's say there were 65 participants. We observed a sample mean of 54.4 and a standard deviation of 10. So we want to figure out the t-score for this. So, dig up your statistics notes if you haven't done this in a while. Remember, t-scores are, you take the sample mean minus the hypothesized mean under the null, and then you divide by the standard error. That is the standard deviation divided by the square root of the sample size. So in this case, if we substitute in all of those quantities that we can find out easily, the sample mean was 54.4. Under the null, the hypothesized mean would be 50. And then we had an observed standard deviation of 10 over the square root of 65. Run through all of that arithmetic, you're going to get a t-score of 3.55. So that's actually all we need. We need that t-score and the sample size, and we can go in and do a Bayesian t-test. Let's do it. Let's go to JASP. Okay, so here's JASP again. Once you open it, because we have summary statistics, we're going to use the summary statistics module. Okay, and here, remember last time in lecture 4, we went to the Bayesian correlation. This time, we're going to choose one of these t-tests. Now, this is a one sample t-test, but you'll find out that the rest of them work very similarly. So we're going to use the Bayesian one sample t-test. So just like before, the summary statistics module is asking us to put in some summary statistics, namely two things. What was the t-score, which we found that was 3.55, and the group size or sample size was 65. So once we put those in and hit tab, you'll notice over in the right-hand side, we're going to get some stuff. Let's take a look at what we get first. So there's, again, just a re-representation of our t-score and our sample size. Here is the Bayes factor. Okay, this Bayes factor is BF10, so this is a Bayes factor in favor of the alternative. It's 34.7-ish, so it tells us that the observed data are 34.7 times more likely under H1, the alternative, than under H0. You'll notice an error percentage. What is that about now? Well, remember, this uses the router version of the Bayes factor, which requires you to perform an integral. So JASP is actually having to do some computer approximation of this complicated integral, and that's where that error comes from. But you'll notice it's very, very small. This is a 4.579 times 10 to the negative 8. So that's like 7 zeros before that 4. That it's basically it's really, really accurate. So don't worry. It also gives you the p-value, of course, which we don't necessarily need here since we're doing a Bayesian test. Okay, so that's enough to begin doing some basic reporting, but we want a little bit more, right? Let's go back over here and let's see. Let's check our alternative hypothesis is the two-sided one. If we had a positive, an increasing alternative or a decreasing alternative, we could also select that. In this case, let's click the prior and posterior plot because that's always an informative thing. And let's give JASP a chance to construct that for us. Okay, so let's walk through this. Once again, it gives a very nice representation of your Bayes factor, both in favor of the alternative and the one that's cast in favor of the null. Remember, these are not different. They say the same thing. 34.70 is just the reciprocal of this number right here. It just reports both of them. Got your pizza plot saying the data is way more likely under H1. We also have some estimation stuff here. We have the median of the posterior distribution for delta, and then the 95% credible interval on that distribution. Let's look at the prior versus the posterior. You see the dashed line looks almost like a normal distribution. This is actually a Cauchy distribution. We'll see how to move that around in just a second, but that's the Cauchy distribution. And then the posterior distribution is your solid. And what you'll notice particularly is that after seeing the data, the probability or our confidence that our belief that the effect size is 0, that is the null hypothesis, it goes from here to here. It decreases after seeing the data. So and how much does it decrease? It's the Bayes factor. It decreases by a factor of 34.7. So this is that Savage-Dickey method once again. So that's what this prior and posterior plot is showing us. We're going to translate all that into a write-up in just a second. I want to show you can also do the Bayes factor robustness check. So what that does is compute the Bayes factor that you would obtain over a wide range of widths for the Cauchy prior. So this one takes a little bit of computation. You can see that across a reasonable range of widths for this Cauchy prior, you get your evidence, your Bayes factor in this strong to very strong level. So qualitatively, we're pretty confident that we've got good support for the alternative. That is that there is a change in the scores for this training group compared to what we would expect on average. Okay. The last thing that I want to show you here is if you click under the prior box, you can actually change. So the default Cauchy has a scale of 0.707. That seems kind of random. That's actually 1/2 the square root of 2. Okay. The technical reason for that comes from some later work of Jeff Rauter, but this is the JASP default, and it is recommended for a variety of reasons. You can also do what are called informed priors. I'm not going to talk about that here, but this does let you move the Cauchy around off of 0. You can do normal distributions. Like remember the very first one, if we wanted to do the mean of 0 and a standard deviation of 1, we could actually specify that here. In fact, you'll see the resulting Bayes factor has changed. Went from 30, I forget what it was 34, it's gone up to 38 now. So again, that just shows that the Bayes factor's value itself definitely depends on the prior that you take. But again, for most purposes, at least in the beginning, it will suffice to use the default prior. Okay? So let's show how to take this output and turn it into a coherent write-up for our research problem. Okay? So I'm using basically the same template that I used in lecture 4. We've got our various elements to report. The first thing, of course, is to report the results of the hypothesis test, which means we need to define the models and specify our prior. So we might say something like this. Under the null hypothesis, we expect an effect size of 0. Thus, we define H0 to be delta equals 0. The alternative hypothesis is two-sided, so with H1 being delta not equal to 0, and prior to observing data, we assume that delta was distributed as a Cauchy distribution with scale R equals 0.707. So I'm just using that default from JASP, and I'm just telling the reader that that's what I'm using. I would much rather do this than to say use the JASP default, because you want to be able to communicate as transparently as possible. If a person's not familiar with JASP, they need to know that this is what the default is. Then, of course, we will report and interpret the Bayes factor. So that's easy. We report the Bayes factor, and here it is. But we should also say what that means. It means that the observed data are approximately 35 times more likely under H1 than under H0. This result indicates strong evidence in favor of H1. Next, calculate and report the posterior model probability for your preferred model. So H1 was the winner, right? The data were much more likely under H1 than under H0. So from earlier, we know that the posterior probability for H1 is equal to the posterior odds divided by 1 plus the posterior odds. Because we used 1-to-1 prior odds, multiplying 1 times the Bayes factor gives the posterior odds. That is, the posterior odds is 34.7. So we take that 34.7 and divide by 1 plus it, so 35.7, and we get a posterior model probability of 0.972. And so we would write that up as follows. Assuming prior odds of 1-to-1 for H1 and H0, our observed data updated these odds to 34.7 to 1 in favor of H1. This is equivalent to a posterior model probability of this. Okay. Now, the last thing we'll do is report the results of the parameter estimation. Again, remember, this is only if H1 is the preferred model. Why? Because if H0 is the preferred model, you know what delta is. Delta is 0. There's no sense in doing an estimation procedure if you know the value already. So, only if H1 is a preferred model. We have that in this case. So what we want to do first is specify our parameter of interest and remind the reader of the prior under H1. So of interest is the posterior distribution for delta, the population level effect size. Under H1, delta was assigned a Cauchy prior with scale R equals 0.707. Again, nothing new, just reminding the reader of what the parameter of interest is. Then we can actually go in and report things. So this comes directly from the JASP output. Let's go back and look at that just a second. Remember, right up here, this gives you all of your estimation stuff, gives you the median as well as the 95% credible interval. Remember, what this says is that there's a 95% probability that the value of delta ranges between here and here, so 0.171 and 0.675. So let's translate that here. The posterior distribution of delta had a median of 0.422 with a central 95% credible interval ranging from 0.171 to 0.675. So all of that is a nice substantive write-up for what we found, which was that there was definitely a positive effect. How big was the effect? It was around 0.42 with this range. We are 95%, there's a 95% probability that the range is between here and here. So decent sized impact of this training program. So that's the Bayesian t-test. The Bayesian t-test works procedurally the same way as the other tests that we've done, the correlation, the binomial, etc. The main difference is you need to know what the prior is for this test. And then for the t-test, it's the Cauchy prior. So once you've got that bit of knowledge and you've got a template here and you have a piece of software like JASP, you can get out there and do your own. So next time we will crank up the conceptual difficulty just a little bit and end the course by talking about linear regression and then analysis of variance. So when we have multiple variables that are predicting your outcome in certain ways, what that's going to do is give us more than 2 models. But we have the tools to and the software JASP to make some good sense out of them. So that's for next time. Enjoy the t-test, use the t-test, and I will see you at the next video.